Okay, so this video is looking at section 4.6 of our notes, and we're dealing with applications of exponents and logarithms, and we're looking at specifically growth and decay in more general terms. And so we're going to be solving exponential equations, and they're going to be in this form. They're going to be in the form A is equal to B times C raised to some power D. And based on what we're looking for, where the unknown is in this equation, we'll have a couple of different approaches. So if the unknown is A is already isolated, so that's great. We simply plug B, C, and D into our calculators, and we get our answer. If B is unknown, then we want to get B by itself, and we'll divide both sides by C to the D, and plug A divided by C to the D into our calculators, and again, just get an answer. If C is unknown, so this would be like x raised to some power 5, let's say. Well, we want to isolate that x to the 5th power, so divide both sides by b, and then we would take, raise it to the reciprocal power, or the 1/5 power, if d was 5. So we'll take the root, right, the dth root. All right, so the first three approaches, we could and probably have solved similar problems in previous sections. It's the fourth one that requires us to use logarithms, and that's essentially the whole point of this chapter, is to get to this point and be able to solve. Now, we've seen in the previous section when we've had to take the logarithm of both sides to solve it. The difference here is that it's a word problem, right? So there's some kind of situation, and we have to set the equation up ourselves. But if the unknown is the d, the x, the variable unknown is in the exponent, this is why we use logarithms. We take the logarithm of both sides, and we'll see that when we get to an example. Okay, so the first part of this, first page of these notes is dealing with interest formulas. Now, we've dealt with these interest formulas before, so they should look familiar. The only difference now is that we can solve for these unknowns up here in the exponent, because now we have logarithms. Earlier in the chapter, when we were dealing with just exponents without logarithms, we couldn't solve this, and we came across a problem where, like, well, we could do an iterative process, but now we'll be able to solve it directly. Okay, so a bank offers interest on money put into their institution. Sometimes the interest is calculated and paid or compounded on a regular basis, monthly, yearly, etc. Sometimes it's compounded continuously. The formula for interest compounding at a regular interval is A equals, now depending on when you get this equation, the A might look differently. There might have a different letter there, but it's essentially the same thing. A equals P times the quantity 1 plus R over N, and then that quantity is raised to the N times T power. All right, so N is the number of compounding periods per year. So if they compound quarterly, then N is 4. If they compound monthly, then N is 12. A, of course, is the final amount. P is the initial amount, or sometimes referred to as the principal. R is the interest rate. It must be placed in as a decimal. And then T is in time, and that's always in years when we're dealing with interest. Okay. Now that's if it's compounding, so what does compounding mean? So I put money into my account. It sits there and just does nothing. At the end of the first month, then they decide, oh, you've earned this much interest in the first month, and then they add it to my account. So at the end of the first month, I put in $100, I might have $102, right? So now that $102 is gaining interest. So the more frequently I compound, the more frequently my account gets money added to it. Now, of course, if I compound monthly, then the amount at the end of that month is not going to be as much as if I compound it annually. So at the end of 1 year, they may give me, let's just say, I put $100 into the account to start with. If I compound annually, then maybe at the end of the year, they add, I don't know, interest rates are pretty low right now as far as how much you get in your account. But let's say they add $4 into my account, okay? So if I did it quarterly, so I put $100 into my account, at the end of the first quarter, they won't put $400 in. They'll put something more like $1 in. So if it's more frequent, the compounding is more frequent, of course, they put less money in, and it's all calculated based on the interest rate and how long the compounding period is. But after the first month, I now have $101. And that $101, that extra dollar, is now gaining interest itself. So the more frequently you compound, sort of you gain money a little bit faster, right? So at the end of the second compounding period, the second quarter, they calculate my interest, and maybe it's not a dollar, it's $1.10, right? Because I had a little bit more money in there, whatever, right? Maybe it's $1.01. Sometimes the difference isn't that much, okay? But that's what compounding means. They stop, they look how much interest you gained since the last compounding period, and they actually add it to your account. Okay, so the more frequent the compounding is, generally that's a little bit more of a benefit. Depending on how much the interest rate is and how much money you have in your account, it may not make much of a difference though. Okay, compounding continuously. This is a formula. A, again, the final amount. P, the principal, the initial amount. E, that's Euler's number, and raised to the RT power. So this is as though there were some magical elf sitting there with an adding machine compounding continuously. So that means every millisecond they're adding a mere fraction of a penny to your account, but it's compounded continuously. All right. All right, so let's look at an example. Gertrude invests money at 7.9% interest, compounded continuously. After 10 years, she ends up with $6,500. How much did she invest initially? We'll round to the nearest cent. All right, so look at your formula compounding continuously. We're here. We're looking at how much she initially, so basically fill out this formula down here. Let's see. So we know the final amount. At the end of 10 years, she's got $6,500. We don't know the initial amount. E to the R, and then you got to put this as a decimal, so 0.079 and times 10. All right, so we're simply going to rearrange that a little bit. Oops, this isn't A, sorry. That's the P, the initial principal. All right, so P is going to be equal, so we divide by this stuff here, right? There's no logarithms necessary here because we don't have any variables in the exponent. Okay, so P is equal to 6,500 divided by E raised to the 0.079 times 10. Okay. So that's really just calculator work. So plugging that into your calculator, I don't know if you can really see my calculator here. It's not really going to work well, I don't think, but let's try. So we are going to just do 6,500, and then divide by, and then you just have to be careful. You have to get your e, so that's your second natural log. So second natural log gives me an e raised to the, and then they put a parentheses in here. So 0.079, and then times 10. Okay, and that gives us, she started with 2,900 and like, well, to the nearest penny, nearest cent, that's $2,949.99. So almost $2,950 almost. Okay, so so that's $2,949.99. Okay. All right, let's go on to number 2. Bank offers 3.3% interest rate compounded monthly. Find how long until $500 becomes $1,000, or it doubles. So interestingly enough, if I start with $5, it will become $10 in the same amount of time. So it doesn't matter. We're really just doubling our money. All right, so we're compounding monthly, so we have to go back to this formula up here and plug in everything we know. All right, the final amount is 1,000. Initial amount, 500. And then we have 1 plus R, our interest rate is 0.033, divided by how many compounding times, periods there are per year, and that's 12 because it's monthly, and then raised to the 12, and then t. So this time the unknown is up here. Okay, so the first thing we want to do is we want to sort of get this stuff by itself. So we're going to divide both sides by 500. When we take the logarithm, we really want one argument on one side and one argument on the other. We don't want to have two things, because then we're going to have the, like, log of a times b, right? We don't want to take the log of both sides and have a log of this times this. And then we'll have log of a times b, and then we're going to have to break that up and have log of a plus log of b. It just makes things easier if we have one thing on each side. So divide both sides by 500, and we get 2. And then, let's see, we want to, let's leave this. We'll do that in our calculators kind of all at once. So I'm just going to rewrite this, and then to the 12t power. Okay. So you can see that if I had started with $5 and asked how long it takes to get 10, I would be dividing 10 by 5 and still get 2. So long as this is twice this, we would arrive at this formula. So really, it doesn't matter. It takes the same amount of time for $500 to become 1,000 as it does for $5 to become 10. Okay? Which is kind of, you think, oh, I start with more money, I'll have more money. Well, you will, but ratio-wise, you'll have the same amount. Okay, so now what we want to do is we want to take the log of both sides. So I'm going to take log of 2. I left a little space here, log of all that stuff. Now, normally I skip over this step because I know, okay, immediately I can use my exponent rule to bring that down in front, my power rule. And so we get log of 2 equals 12t times log, and then this whole thing, 1 plus 0.033 over 12. Notice in this case, I am taking just common log base 10. I could have taken natural log. there were no e's in this formula, so there's no benefit to doing taking the log of base e or the natural log. You certainly can. It doesn't matter. It's not going to make it more difficult, but it's not going to make it any easier. So I just chose log base 10. And remember, I don't have the base 10 written there because if I don't have the base, it's by default base 10, common log. All right, and so now let's just solve this for t. So t is equal to log 2, and then divide by everything here. So we get 12 times log, and then 1 plus 0.033 over 12. All right, so plug that into your calculator. That's really just all calculator work there. And let's see, I get 21.0333. And, you know, sometimes this is pretty close to just one whole year, 21. So we'll just say approximately, remember the squiggly equal sign means approximately equal to 21 years. Okay. All right, let's go on to number 3. So number 3 says, Nooney invests $10,000 at Bank A, which offers an 11% interest rate compounded continuously. Noni invests $10,000 at Bank B, which offers 11% interest rate compounded twice a year. After 10 years, who has more money and by how much? All right, so the first one will compound continuously, and the other one is compounding twice a year. Now we know, I know who's going to have the most money. Everything else is the same. Like the interest rates are the same, the initial amounts are the same. Compounding more continuously gets you more money. And yeah, the interest rate is pretty high, 11%. You know, you'd be lucky to get 3 or 4% in any bank nowadays, and that's because the interest rates are really high. You know, 10 years ago, you get 0.5% in a bank. So you're going to see somewhat of a difference between these two, but not that much considering it's 10 years, right? So the difference in compounding continuously and compounding even twice a year is not that great. It is going to be somewhat significant here just because the interest rates are ridiculously high in this problem. Okay, so Bank A. Why don't you pause this video and do both calculations, and then I'm going to work on them now. All right, so we're not looking for time, so this is pretty straightforward, looking for the final amount, right? So A equals initial amount, principal, $10,000, E raised to the 0.11 times 10. So that's pure calculator work there. So I get 30,000, $41.66. And then for B, Bank B, we get A equals the initial amount, 10,000, 1 plus 0.11 over twice a year, 2 times T, 2 times T, which is 10. All right, again, that's just calculator work. So plug that into your calculator. So I get $29,177.57, both to the nearest penny. And then, so the difference, we would just subtract those. Oh, excuse me. The difference, if you subtract them, is really only $8.64 and $864.09. So not a very big difference when you consider they started with 10,000. it's always going to generate more money if you compound continuously. But if you had a more realistic interest rate, say 2%, you would see that this is dramatically less. It's so high, $800 difference is not that great when you consider it was 10 years, doing it. Okay, but definitely compounding continuously does generate more money. All right, number 4, find the interest rate if $600 becomes $1,000 after 15 years. Assume the interest is calculated quarterly, so compounded quarterly. So pause the video and then work on that one. All right, so we know the final amount is 1,000. The initial principal is 600. We're using the compounding not continuous formula. We don't know R. We're going to leave R as R because we don't know what that's what we're looking for. We're compounding quarterly, so we have 4, and we have 4 times 15. All right. So the first thing we probably want to do is divide by 600. Get that by itself. So that I'm just going to leave this. I'm not going to pick up my calculator kind of till the end here. So 10 divided by 6. Well, let's just leave that. I'm going to leave it as a fraction rather than writing it as a decimal. And then we have 1 plus r over 4 to the 60th power, right? So we want to get rid of that. So we raise both sides to the 60th root. So we take the 60th root of 5/3 to get rid of that exponent over there. And then we can, so I guess we don't really need these parentheses since I'm no longer raising it to a power. We're going to get rid of the 1, subtract 1 from both sides, and then we will multiply by 4. So r is going to be equal to the 60th root of 5/3, and we're going to subtract 1, and then take the whole thing and multiply it by 4. So the 60th root, how do you do that in your calculator? You, depending on the calculator you have this button here which has an X, it looks like an X root thing, right? So that's really what you want to do. You just got to play around with it, how to use it. So let's see, we're going to do, I think what we want to do is 60 first, 60, and then hit that button. So that turns, it doesn't really look like it, but it turns that 60th into that. All right, and then under the parentheses, under the radical, we'll do, let's put it in parentheses just to be safe. 5 divided by 3. All right, we get that answer. We subtract 1 from that answer, and then we multiply that result by 4, and we get our answer. So our answer is 0.034200. All right, we'll leave it at that. And then, okay, so then it's about what, right? So we're doing it as a percent. If we say 3.42%. Now, another way you could do that root is use your caret button. So we want, let's do 5 divided by 3, close that parentheses, raise that 2, and then start a new parentheses, 1 divided by 60, right? So raising it to the 60th root is the same as raising it to the 1/60th power. So we could do that, subtract 1 again, and then take that result and multiply it by 4. Let's see how that does. Yeah, same answer. Okay, so to get your 60th root, you could either use that button or think about raising 5/3 caret to the 1/60th power, right? So you could do that either way, okay? Put the 60 first and then hit this button, or 5/3 raised to the 1/60 power.